Okay, everyone, we're going to talk about GD&T now, and we're going to talk about degrees of freedom. You know that we have in our input sheet, and let me pull that up real quick. In our input sheet, we have datum A, B, and C. And this is called a datum reference frame. So I'm going to talk about degrees of freedom in a second, but when you have three different directions, it takes away degrees of freedom. It essentially stabilizes the part so that you can make repeatable dimensions. So I'm going to go right here. I have to go to that actual thing. All right, so you see this? What if this were our swivel stop? A datum reference frame allows the part to sit on its primary datum. That would be like my surface plate here. And then I would have two angled plates that are absolutely 90 to my surface plate. And the order in which they're in the feature control frame tells me what contacts what first. And that is very important, because if you do not set them up in order, you can allow good parts to be rejected and bad parts to be accepted. So you really, really want to get the order right. So we have these, and I don't know where these angle irons are, but these are very, very accurately ground fixtures for inspecting parts. So why do we have these? This is a picture of a surface plate, and this is gray granite, and it's extremely accurately ground down to microns of an inch. So is this, and it's extremely 90 degrees. It's extremely accurate in its 90-degree angle. So we set that on the surface plate so that we have a good 90-degree angle here, and this is extremely flat. So these are examples of other fixturing devices where we could actually hold something down, or we can fixture things with them and measure to them. So these tools are what we use. We use this for what we set something down on, and then maybe two other planes to make sure that that part is not moving when we inspect it. So what I'm going to do now is I'm going to talk about degrees of freedom. So we know that we have 6 degrees of freedom. And I'm going to turn on the video here in a second. We have movement in the X, Y, and Z. And then we have rotation in the X, Y, and Z. So what I'm going to do now is I'm going to move over to video. And I'm going to stop presenting. And I'm going to show you. Yeah, you have a question? I was not. I was just showing that presentation. I'm about to show it now. So can you see it now? So you have a question? Alexander?
Sorry, I didn't realize that my mic wasn't picking up anything.
Oh, go ahead.
There was a gentleman that was there. I think his office is like directly to your right, that first office. I don't remember his name. But he was in there, and he was referencing one of the machines having a 4th axis.
Yes.
How does that? I don't understand how that's possible.
Okay. So let's talk about 4th and 5th axes. So if I have this part, it can move along the X. If I have a machine, it can move along the X. The machine can move along the Y. And then the machine can move along the Z, right?
Yeah.
And then we have rotation. We have rotate. So when we have a 3-axis machine, it's only moving in 3 directions in translation. It's not rotating. So it's moving this way.
So this, so this is like, it can go underneath the part?
No, what it does is it pivots the part so that you can machine in a different axis. The fourth axis allows the rotation of how you're holding the part. It allows you to rotate it. So
That's the part that I didn't understand, because I was thinking without manipulation of the piece, I was like, how is that possible to have another axis?
right. So we still have the X, Y, and Z that the actual machine head is moving along, but the entire fixture can pivot so that you can machine on another side without refixturing your part, which
Right.
is huge. That's huge. So imagine a 5-axis, it could turn this way, and maybe it could turn this way too.
Yeah, that makes sense.
So a 5-axis machine, 6-axis, 7-axis, that's getting extreme. And what it does is it just saves you a lot of time of setup. You don't have to have multiple fixtures for doing things. You could just flip the part apart. You don't have to flip it over and have another fixture to hold it down in another direction, in other words. Does that make sense?
What would the seventh be?
Oh, maybe the whole machine turns over.
Yeah, that's what I'm saying. I was like thinking to myself, I was like, how does that make sense? That's
So
crazy.
what if it turns on an angle on a z-axis? You just
Oh,
have to look those up. So
that's getting
different
crazy.
machines have different capacities, and I've seen the largest 7-axis mill in the world. That is used for carving stone, and it is on an arm that comes down, and it has a fully articulating head that can go around a machine like freehand, and it's all programmed, and it's right here at Escobedo Construction in Buda. It is a cool machine. I have some pictures of it. I have to bring them up and show them to you. All right, I'm down on my knees here, but let's talk about degrees of freedom as it pertains to a datum reference plane. The datum reference plane, if you look at your input for the swivel stop, has datums A, B, and C. And it doesn't matter in what order those are put in that reference frame. It could be CBA, CAB, whatever, D, K, Z, it doesn't matter. You have as many datums on your part as necessary to fully control or inspect your part the way you need to, depending on its function. So I am going to tell you something. The datums that you see on a part are the mating faces that mate that part in the assembly. It makes sense, because why would I dimension something or fixture something on the bottom of this part if it didn't connect to another part on that face? Counterbores will never be your connecting face. It will always be the opposite side. So if I have counterbores on the swivel stop, the bottom side is what connects to another part. That's my datum A. So let's talk about degrees of freedom real quick. Let's say this surface plate is a magnet, and this is a piece of metal. If I set this down on that magnet, it cannot now move up and down, so I've taken away 1 degree of freedom. It also cannot rotate this way, that's 2 degrees of freedom, and it cannot rotate this way. It can spin, but it takes away translation in the Y and rotation in the X and rotation in the Z. Just by setting that down on there, it can't do that. If that were magnetized, it couldn't angle, right? It couldn't lift off. So setting something on its primary datum takes away 3 degrees of freedom. So I have 6, right? The right-hand rule. Woo. All right. Movement and rotation in the X, movement and rotation in the Y, movement and rotation in the Z. Now, if I am taking away 3, I've got 3 left to fully fixture this part. So let's say I push it up, this is a magnet too, and I push it up to this one. Well, now I've already taken away 3 degrees of freedom on this. It can't move this way anymore. So that's 1 more degree of freedom. So this secondary datum, this is primary, takes away 3 degrees of freedom. I just set it down there. There are 3 degrees gone. Secondary datum, push it up against there. It takes away that translation. Now can it spin on the z-axis? Nope. So now all my rotation are gone and 2 translation are gone in the y and in the x here. So I can still move it this way. There's only 1 degree of freedom left. I could just slide it. So when I bring my tertiary or my third datum in, and that's a magnet, it slips up there, I now have a datum reference frame. And this is usually longer to establish points of contact. So I've taken away all 6 degrees of freedom. This part is extremely stable. And now I measure from these planes on my metrology tools to the locations on my part because the edges of my part are not perfect. I also see if my holes are perpendicular to this and my planes are perpendicular to this. So setting up in a datum reference frame establishes repeatable, repeatable measurements, okay? So repeatable measurements, I have a datum reference frame of 3 planes. That takes away 6 degrees of freedom. What if I had a circular one? We'll talk about that later, a circular part. But now let's talk about the datum reference, the feature control frame, and I want to talk about that real quick. So I'm going to stop this, and we're going to talk about that. Let me unpin myself. Right there. So we have our datum reference frame. We set our part down in there, and we could not move it. And I want to talk about positional tolerance. So positional tolerance is, to me, it's not hard, but a lot of people find this to be the most complicated thing. All right, can you guys see the screen? All right, let me see. I got to present. Sorry about that. Keeping me on my game. Can you see it?
Yeah.
All right, thanks. So when we have something called positional tolerance, we're trying to locate this hole. We get these things called basic dimensions, and they're in a box. So if you look at the other dimensions, they're not in a box. When a dimension is not in a box like this, then we go to the tolerance block for our tolerances. So why don't I go to the tolerance block for my tolerances of the location dimensions of this hole? Because this is positional tolerance, and this is the positional tolerance right here. This is how much it can move. So we don't want you to go down with plus minus tolerances down to the tolerance block. We want you to look at the feature control frame for how much it can move. And that's how much it can move right there. So we put these boxes around here, and that's called a basically perfect dimension. It's called a basic dimension. It's theoretically perfect location. So we're not really locating the hole there. What we're locating when this is theoretically perfect, the only thing that we can make theoretically perfect is we put this cylindrical tolerance zone right there in the center of that hole. And if that axis stays inside there, it's great. If it doesn't, sorry about that, right? It's got to be reworked. So why would an axis that was on one side, let's say on the top side of this part, be inside there, and in the bottom side of the part, let's say I had this diametric tolerance zone here, and I have an axis that's here, but then before the end of the part, it came out like that. Why is that wrong? And what does that do? So the angle of the hole is not held within this cylinder. Do you see that when I have an axis that goes right here, we're actually perpendicular to A. So I've got a perpendicular, indirect perpendicularity or angularity with that axis being inside this tolerance zone. So when this axis goes so it controls the angle just by staying inside this tolerance zone somewhat. It can angle within 0.03 diameter. I don't have to think about angles anymore. All I know is 0.03. So that's how much my axis can move from one side to the other. Now, if it goes beyond that, then it's out of spec. So this right here, position of an axis, indirectly, what does it have to do? So if we look at the relationship right now of the axis with datum A right here, what orientation is it to datum A? It's perpendicular. So position actually indirectly controls perpendicularity to datum A. Datum A is my surface plate. And to make something stable, I have to have at least 3 points of contact. Like a tripod, to be stable, it has to have at least 3 legs. So this is the 3-2-1 rule. You remember it took away 3 degrees of freedom when I set something on the surface plate? 2 degrees of freedom here and 1 degree of freedom, and that equates to 6, and it is completely locked down. So that tells me I'm going to set it on datum A first. This position is called primary datum, although there's 3 points of contact like a tripod, right? It's going to be stable. When you set that down on something, it's going to be stable. Now, what do I have in datum B? Well, I don't care how curvy this part is. If it touches at 2 points of contact here, it's going to be stable and it will not pivot. It also takes away 2 degrees of freedom. And I'm sorry, that's the wrong side for datum B. It could be this one. So let's do it like this. And the 2 high points are going to touch right there. So it has to touch at least 2 points. On datum C, this could be tangent. I don't care. It could just touch at 1 point. But that will stabilize it because it cannot translate in that direction. So the 3-2-1 rule tells us how many points of contact. It tells us how many degrees of freedom. The order in which you put these datums in here tells you the order in which you should set things down. So I'm going to set it down on the surface plate, slide it over to B second, and slide it up to C third. Those do not have to be in alphabetical order, and they don't have to be. It could be Z, A, K. I don't care what it is. It's the order that you put these in here is stability, secondary, most important location. Third one is just locking it down. Now I've got a diametric tolerance zone right here that is absolutely at 1, perfectly to tool makers' tolerances, not to the tolerance block. That's why we put those basic dimensions on there. And if you want to know how much tolerance you have of position, because these are position dimensions, they're location, right? Then this tells us to go and look over here. So I know that I have a tolerance of 30 thousandths in diameter, which gives me 57% more tolerance zone than a square one, a plus minus tolerance. Now there's something right here that I want to talk about, and that's our maximum material condition. When we talked about the maximum material condition, when I have a hole, and this is on a feature of size, right? It's on a hole. And let's say that it could be as large as, with this tolerance, 1.02, and as small as 1. Is everybody muted? Because I'm getting some weird feedback. And as small as 1. So with these two sizes of a hole, this is a negative feature. I call it we're removing material by making the hole. Within these two sizes of the hole, these are the extremes, the largest and the smallest hole. Which one allows the part to weigh the most? Would that be the largest hole? Or the smallest hole allows the part, the entire part, to weigh the most? The smallest hole takes out the least amount of material from my part. So that is my maximum material condition is 1 inch. Okay? That's at one extreme of the tolerance. So you get MMC and LMC from your tolerances. All right. So now I'm going to show you guys something else. And this is a little bit extreme, but we're going to talk about this. This tolerance only applies at MMC, which is the smallest hole. Well, what about the largest hole? As the hole gets, this is my worst case, is smallest hole and the largest pin, right? As the hole gets bigger, this tolerance can increase. That's called a bonus tolerance when you see that. When you get a bonus at work, it's a positive thing. So what I'm going to do here is I'm going to put the GD&T on the drawing, but I'm going to show you an example of bonus tolerance right here and why we have that. So let me... Are you guys all muted out there? Because I'm hearing somebody yelling. I'm going to mute whoever's on your phone. Okay. So here we go. I'm going to show you guys something again. Okay. So let's talk about bonus tolerance. I'm going to get a couple little things real quick, and I'll be right back. Let me get some props. Okay, this is extreme, but I'm going to show you. Let's say that this is the smallest this hole can get. And I have this feature is the largest that's going to go through there. All right, so I can only move so much. So only, let's say that this is fixed somewhere and this pin is fixed to something else. It better not move too much or it's going to interfere, right? So we have 0.03 in the drawing that I just showed you, tolerance of that. Well, what if this same hole got this big and this is fixed? Does it still have to stay that precise? It can move a lot more. This hole, the hole itself could move a lot more in position and still hit this pin. So at the smallest hole, I better stay very precise to hit this pin, right? But as the hole increases, then the hole can move more and still hit the pin. This is an extreme exaggeration, but that's what that call out is telling us. So let's go to our drawing, and I'm going to turn off my video. We're going to finish our drawing, and I'm going to show you what I mean. Okay, We've got some GD&T to apply, and we've got a continuous feature symbol to put on. So I'm going to go to Symbols. Sorry, this is so large. I'm going to put on my datums. Datum A is my surface plate. It is the bottom of the part. Datum B is this side right here. So I could put it on this extension line. I could put it here and move my dimensions out. I might put it just on this extension line, and I can move it down in a sec. So first you want to put it on the line and then move it down. You cannot put it on where there is nothing. There's nothing in space like that. So this is datum B, not at the end of the arrowhead. Exaggerate that. It can be on this surface. It can be on an extension of that surface. Datum C is the top. So I'm going to put that datum in. That could be over here. It could be here. And so that's datum C. Now I'm going to put a feature control frame over here. And it's going to be beside this hole, but I'm just going to set it out in space, right click and continue. So I don't have that arrow. This is positional tolerance. And I've got a diameter of what? Let me look at my input sheet and move this over. Diameter 0.035, maximum material condition. We cannot have maximum material condition on a threaded hole because the tolerances of size are thread maker's tolerances, and they're not, we don't have a plus minus tolerance. We don't have a maximum and minimum. So we have just a regular hole. It's 0.035. We put our, so this tolerance right here applies at, you hit this drop down, at the maximum material condition when that hole is the smallest. So at the diameter 0.50, the MMC, or our worst case, is 0.48, the smallest hole. So at 0.48, this applies. At 0.52, this tolerance gets bigger by however much it moved away from MMC. So at 0.52, I could add 0.04 to that. That would be 0.075. So this allows this tolerance of position to change with the feature of size, which never happened with plus minus tolerances. So A, B, and datum C. And that's the way we're going to set that up in that feature control frame, first, second, and third. And this is our tolerance all in one block, and it's positional tolerance. So what I'm going to do is I'm going to move this. We'll talk more about positional tolerance. It's kind of a hard topic, that bonus tolerance. All you have to know is if someone asks you, what is that MMC? That's bonus tolerance. That means as the hole gets to a better scenario, which is getting bigger, it can move more. It gets more tolerance of position, so it can move more. And that's a good thing. All right, why hold it so tight if the hole is huge? So we've got those things. We have to make these basic dimensions. I'm going to double click on the one, go to precision and tolerance, and there's basic right there. Precision and tolerance, basic. Everything that locates those holes that have positional tolerance on them has to be basic. So we also have indirect perpendicularity to datum A within 0.035 inches diameter of a cylinder. So that tells me it can angle by 0.035 inches. I don't have to know the degrees. All right, the last thing I need is that continuous feature symbol right here saying that I have a plate that I'm going to slide up against this, and I'm going to measure from this end to the plate as if it were still a continuous feature. So insert sketch symbol. If you go to drawing resources, sketch symbols, there's a continuous feature. If you want to insert one, hit the top button of this. Continuous feature. Scale of 1. If you have a leader on there, take it off. And I'm just going to say okay. And I'm going to bring this down, and I'm just going to eyeball setting that at the end of that extension line. And hit escape. And I believe now our drawing is complete. I'm going to go back and look at my input sheet. We've got this 2x. We've got our 2x on our radius. We've got our MMC at ABC. We've got our datums in there, A, B, and C, and we got our continuous feature symbol. All right. So what I'm going to do is I'm going to back out of this, double click my middle mouse button. I'm going to save it, file, export as a DWF, express, publish. And I'm going to make this a -V for verification and save it. Always review your work to see if you had forgotten to arrange dimensions or whatnot. And then you're going to submit. Okay. So I'm going to go in and put your due dates in, you guys. Go ahead and turn your bracket in for verification as soon as you can. And I'm going to set the due date for the actuator base. And let's do the bracket for Thursday. That'll keep me on point. The verification for this is due the end of the day on Thursday. Thank you, guys. Sorry about the long videos.
All right, no worries. Thank you.